Greenwood, who is our expert, and will take you guys through step code today.
Thank you. Thanks for joining us, everybody. Let's just get the presentation up here. Okay. So, guys are probably familiar a bit with the step code already and all the different steps. So, we're just going to go into a little bit more detail on some of the metrics that to reach those steps and some things that are involved and some things to take into account when you are engaged in new building. So won't go over too much about what the step code is because you're probably familiar with that already.
My name's Sean. I wouldn't mind if you go through that quickly.
Sure.
That wouldn't bother me.
Okay.
The other viewers and all.
Yeah, no problem. Then no problem going through that a little bit. So we go through the step code, talk a little bit about net zero ready homes, what that means, working with an energy advisor and what that entails and how that can help with new builds. The Builder Guide web tool, which is a really important resource. It's an online resource, and honestly, that's where a lot of this material that I'm going to be presenting today came from, was the Builder Guide web tool. And so we'll talk about the step code metrics, airtightness, equipment and systems, and the building envelope, your prescriptive versus performance path, the MEUI, TEUI, TEDI, and GHGI. These are all different metrics that can be used to help you reach different steps. We'll go over those a little more in detail. Mechanical use, or mechanical energy use intensity, thermal energy use intensity, and the like. We'll talk about airtightness and why that's important. Talk about some principles of high performance buildings. Talk about some of the different climate zones and what climate zone we're in. Mechanical equipment, examples for Part 9 buildings. Insulation and R values and building assemblies, windows and doors. Won't go into too much detail about that. And then detailing and sequencing, why that's important, what those things are, and mechanical systems and equipment. So here's a little bit about the step code. What it is, it provides a consistent provincial standard for the energy efficiency requirements of new buildings. It uses tiers of performance targets instead of prescriptive requirements such as R value and U value in windows that builders may be familiar with. So there's a need for education resources for builders and specifiers on this new performance-based system. The Builder Guide, which I'm going to be drawing a lot of this presentation from, to the BC Energy Step Code has been developed to clearly communicate the step code and how to achieve its performance targets. The target audience for this guide includes builders, designers, and building officials, though its content has been developed to be accessible to any reader with a basic knowledge of wood frame construction and building design. So we have the two parts, the two types of buildings, Part 9 residential buildings, less than a 600 square meter footprint, and greater than 600 meter square footprint, and Part 3 low and mid-rise residential buildings, which most builders will be engaged in less than 3 to 6 stories, less than 600 square meter footprint. Okay, so here's the steps, step 1 to 5. So you see step 1 is basically building to the BC Building Code as it stands now. And that's your basic reference house, the EnerGuide rating system. So when an energy audit is done on a house, it gets an energy rating. And that rating is comprised of the insulation values of the house, the heating system, and the air leakage results. Also, the windows and doors, that kind of thing. So step 2 is 10% more efficient than your basic reference house. Step 3, 20% more efficient. Step 4 is 40% more efficient. And then step 5, you're getting towards net zero ready. And then with part 3, the wood frame residential, you have step 4 is net zero ready, and step 5 would be, you know, a greater performance than that. So here we go. Net zero ready, what does that mean? So this provides, the step code provides a path towards a performance-based transformation from current energy efficiency requirements to net zero ready buildings by 2032. Province is committed to taking these incremental steps as part of its commitments to improving energy efficiency in the built environment. The path to net zero ready is set out through a series of requirements for energy use, thermal energy demand, and air tightness. Performance requirements that have been set were the result of lengthy consensus among several key stakeholders from across the province and supported by energy modeling and analysis. The process of establishing the step code took a period of about 2 years through the efforts of Energy Efficiency Working Group and the Energy Step Code Council and is ongoing. So what is net zero? It's a building whose annual energy requirements are minimized and could be offset by renewable energy. Of course, you know, net zero ready is a little bit different than actual net zero. You know, net zero, that's a house that's producing as much energy as it consumes. And a lot of times you're going to see renewable energy being used to get to that goal. So step code around the province. The step code applies across the province. One of the central purposes of the step code is to provide province-wide consistency in building energy and emissions policies and bylaws. As of December 15, 2017, all authorities having jurisdiction who enforce the BC Building Code can opt to require or incentivize levels of the step code. So you've seen this. There's a bunch of communities that have adopted this already. The Regional District of East Kootenay has adopted it. The City of Kimberley has, City of Nelson, and so builders who are building in those areas can get incentives if they reach the different steps of the step code. It doesn't apply in the City of Vancouver, and it doesn't apply in federal lands within the province.
Do you know, does it apply to Fernie, Sean?
It doesn't apply in Fernie currently.
Okay.
No, they haven't adopted it yet. But it is in the regional district, so as soon as you get outside the city limits, well, I guess going towards Cranbrook, but
Ski Hill, for example.
yeah, Ski Hill, exactly. There's going to be step code requirements there. So the step code has mandatory energy modeling at all steps for all building types. So, you know, it starts off with you're going to model, or an energy advisor is going to model the house based on the plans that are provided. And that's going to happen in HOT 2000, which is the energy modeling software. So, you know, a house gets modeled and you're going to know pretty quickly which step it's going to reach, you know, just with the proposed building plans. So energy modeling, it's integral to confirming that the design meets the targeted energy performance requirements. So say, for instance, you know, you see a plan, you model it, and then you realize, well, the direction that the building is facing may not be optimal. It could be just a matter of, you know, switching that direction to orient it in a different manner. It could be a matter of switching out the mechanical equipment. It could be a matter of increasing certain insulation values. I mean, the way that the building code is set already, you know, you're probably going to reach at least step 2 just by building to code. There's other benefits to performing whole building energy modeling, such as assessing which design measures have the most or least impact on energy performance. Basically, you know,
Sorry to interrupt.
go ahead. Yeah.
Folks just can't see the screen here, so they can't follow your PowerPoint.
Okay.
Would you mind taking 2 seconds just to email it to me and I can
Oh, sure. Yeah.
Sorry, folks.
No
we're
problem.
Just gonna get that PowerPoint out to you.
Yeah, so people can follow along for sure.
Sorry, Sean.
No, that's fine.
New
I
system
will
we're not used to using.
just forward this to you, Helen.
Thank you very
No
much.
problem. There we go.
Thank you. Okay.
Should be on its way electronically.
Perfect. You can go ahead and cut up here.
Yep, no problem. So energy modeling can be used to refine designs and find the most cost-effective approach for achieving a desired outcome. The modeling outputs for heating demand are also useful for sizing mechanical systems and preventing oversizing equipment. So yeah, you can see that's going to be important. So what are the step code metrics? What are the key metrics here? They can be separated into 3 categories: air tightness, equipment and systems, and building enclosure. When we talk about building enclosure, that's closely related to the air tightness, your air barrier. And we're going to get into a little more in detail about why that's so important to have a continuous air barrier. Air tightness and building enclosure metrics direct the building design toward an enclosure-first approach, which is integral to minimizing heating demand. So that's part of that air barrier, continuous air barrier. Equipment and system metrics consider the total energy consumption of the building. Performance metrics for Part 9 and Part 3 buildings have some overlap, but there's also slight differences. So the Builder Guide web tool, where a lot of this presentation is drawn from, is also available as an online web tool. Interactive interface enables the users, designers, builders, and building officials to quickly find topics relevant to their climate zone, their target step, and building type. The web tool, as well as the BC Builder Guide, has been developed specifically for wood frame Part 9 homes and wood frame Part 9 and Part 3 low and mid-rise residential buildings. The guide provides an overview of enclosure types, mechanical efficiencies, and design features and strategies that may be used to reach each step within each climate zone in BC. So we're in climate zone 6, if you didn't know that already. And so there'll be specific metrics in that climate zone in the Builder Guide web tool. These principles may be used more widely than for achieving the step code targets, as they demonstrate the best practices in the industry. So what is a prescriptive versus performance path in new house builds? Current compliance for Part 9 buildings prescriptive path. The building is to be designed and constructed to comply with prescriptive requirements in the BC Building Code, subsections 9.3, 36.2 to 9.36.4. And that's set out in the BC Building Code. Step 1 compliance building to be designed and constructed to comply to the percentage lower than reference house performance target as set out in 9.36.6. Both energy modeling and air tightness testing are required. So, in the past, if you could just build it to code, you didn't necessarily need an energy advisor or modeler to tell you which step you're going to reach. You're probably going to reach step 1 or 2, no problem. But when you do the energy modeling, you can kind of know ahead of time before you start building which step you're likely to reach. So step 2 to 5 compliance building is to be designed and constructed to comply with step code performance targets. These targets include air tightness requirements, maximum energy used by the building equipment and systems, and maximum thermal energy demand. Energy modeling and air tightness testing is required, and the construction must be revised for compliance if the energy targets are not met. So one thing you can do, it's called a mid-construction blower door test. So that's before all the exterior siding is put on and before the interior finish, like the drywall or whatever you may be using, is put on. And that's a point where you can really find out if you have air leakage, if you don't have a continuous air barrier, and that's a step where you can easily, address those issues before, all the siding, all the finishing is put on. You can find out where the leaks are coming in and address those things. So here's a few of the things that are used to reach certain steps. So when an energy modeler is modeling the house on the energy software, they're going to look at mechanical energy use intensity. That's one of the metrics. So MEUI, it's the metric for mechanical and systems energy use over a year. It's estimated by using an energy model in accordance with BC Building Code Article 9.36.6.4, normalized per square meter of area of conditioned space, and is expressed in kilowatts an hour over square meters per year. The mechanical energy use intensity includes space heating and space cooling, fans, service, water heating equipment, pumps, and auxiliary HVAC equipment. The MEUI metric includes additional allowances for buildings with floor areas equal to or less than 210 square meters, 2,357 square feet. It sometimes gets a little complicated because all this energy modeling is done in square meters and most building is done in square feet. Yeah. And so translating those can sometimes be confusing. Additional allowances are also provided for buildings which include mechanical cooling in at least 50% of their floor area to remove a barrier to provide cooling where it is necessary.
For Sean,
Yeah.
is that main floor or is that total conditioned area?
It's total conditioned area.
You've got a finished basement and a main
Yep.
floor, so that's both?
Yeah, that's right. It's going to take into all account the whole square footage of the area. But it does exclude electrical loads such as miscellaneous receptacles and lighting. So now you have total energy use intensity, which does include the receptacles, appliances, and lighting. So it takes into account the previous one, the mechanical energy use intensity, your space heating, cooling, fans, service water and heating equipment, but it also includes receptacles and appliances and lighting. Yes, thermal energy use intensity includes electrical loads, miscellaneous receptacles and lighting. So now you have TEDI, which is your thermal energy demand intensity. So it addresses energy gains and losses through the building enclosure. TEDI limits the annual heating required by a building for space conditioning and for conditioning of ventilation air, estimated by using an energy model, normalized per square meter area of conditioned space. TEDI considers thermal transmittance of the building enclosure components, including assemblies, windows, doors, skylights, solar heat gains through building enclosure components, mostly windows, air leakage through the air barrier system, internal heat gains from occupants and equipment, and heat recovery from exhaust ventilation. So it considers the same factors for Part 9 and Part 3 buildings. That's going to be the same there. So this metric isn't used per se by the STEP code, but it's something that we can also calculate, which is your greenhouse gas intensity. It's the total greenhouse gas emissions associated with the use of all energy utilities on site. So again, it's not part of the STEP code. The City of Vancouver uses it as an additional metric for rezoning requirements. But it's kind of a nice value to know about. The metric is reported using kilograms equivalent of CO2 emissions per square meter area of conditioned space. So how do we achieve these targets for the TEDI, for instance? So one of the important metrics is building form and exposure form factor. Form factor refers to a building's overall shape, form, and size. A building's massing is central to achievement of TEDI targets. in that the more complex a building shape, the greater the number of opportunities for heat loss through the enclosure. Building with several complex junctions and corners will lose far more heat through the enclosure than a building that has been designed as a simple solid form. Form factor can also be assessed in terms of a building's vertical surface area to floor area ratio, VFAR. A lower VFAR indicates a lower overall potential for heat loss through the enclosure, as buildings' vertical surfaces, for example walls, tend to have lower R values than vertical surfaces. For example, roofs. Higher VFAR values are often a function of the building floor plate size as well as the level of articulation or complexity. So here are some examples of different building shapes. You have, simple form results in a low VFAR, moderately complex form results in mid-range VFAR, and a complex form results in high VFAR. So if you're going to have that higher VFAR, you're going to need better building enclosure, better sealing to the joints where junctions and different angles meet. So here's a little bit of a table showing how to reach the different steps with different metrics. So your air tightness, air tightness is a pretty big factor. If you're going to have to reach at least 2.5 air changes per hour. That's what these values are on the left-hand side, 3.0. 3 air changes per hour is pretty standard. 2.5, most new buildings are going to reach that or under, unless the building envelope has been severely compromised. 1.5 or under, you're going to reach step 4. 1.0 or under, you're going to reach step 5. That's a really super tight building envelope.
Does that include if you have an HRV or other air exchange system?
Yeah, it does. And honestly, I think that's mandatory now.
Yeah.
For the building code. You do have to have a mechanical ventilation system of some type, whether it's an HRV, ERV, or just a whole house ventilation system. Yeah.
It's interesting that the HRV provides air turnover.
Yeah.
And you're rewarded, the objective is to minimize air turnover.
That's right. That's right. So, part of the issue with a really low air leakage is you don't have enough natural air outside air replacing your indoor air, which can be an issue with brand new builds because you've got fresh paint, maybe even fresh carpet, and they're off-gassing. Yeah. You want to have ventilation to,
VOCs and everything that's...
Yeah, deal with those VOCs, exactly. And so, when the building is fully constructed and all the mechanical equipment is installed, there is going to be an air test done. And it will take into account all those penetrations that, have been created by installing these systems. And if they're installed properly and well sealed, then air leakage shouldn't be a huge issue. And then, so when you have a really low air leakage rate, then you want those mechanical systems to be working to bring in that fresh air.
Okay.
Yeah, and hopefully they don't compromise your air barrier.
So that number of air tightness and getting down to less than 1, for example, for step 5.
Yep.
That assumes none of the mechanical systems are operating, and that's just dealing with...
Right, exactly. And so when the air test is being performed, none of those mechanical systems will be running.
Right, okay.
Yeah, for sure. So a little deeper into the metrics, and you can find this table in the Builder Guide web tool, which gives you a rough kind of guide on whether you're reaching your metrics or not. And, this is kind of a handy thing to have. And this is something that is going to be calculated with the energy modeling software, right? And it will tell us, whether we reach these targets are not. The only unknown will be the air leakage results, and that'll kind of be the final thing that'll let us know whether you're going to reach, say step 4 or step 5, whether you've hit 1.5 air changes per hour or below 1. So here's another important factor in reaching these targets. It's called solar control and orientation, and it's mostly about windows and where they're placed. Also how the building is situated relative to the site. So solar control should be considered for windows and glazing exposed to direct or reflected sunlight to reduce potential overheating and cooling equipment needs. The potential for overheating varies by building, climate zone, and exposure. Solar orientation. So your orientation refers to the alignment of a building's principal axis. Buildings that are oriented to maximize the potential for solar gains through glazing from the south can reduce the heating demands. This strategy does not reduce heat losses, but makes use of passive heat gains, which may help achieve the TEDI requirements. Building orientation can also be used to reduce lighting needs by taking advantage of natural light, which can help to achieve TEDI targets as well. To maximize the potential for solar gains, the longest facade of a building should be oriented to face as close to due south as possible. Ideally, the south-facing facade should be within 30 degrees in either direction, east or west, of due south. While many sites are constrained by existing lots and street grids, there are still opportunities to orient the upper floors of a building to the south. Solar shading strategies should be incorporated into the design to avoid overheating in summer. So whether that's something like retractable awnings or overhangs, that should be considered as well. So here's some examples. These are buildings. You have the south that, as you can see, the north is up, south is down, kind of like a map orientation. So in building A, it's non-optimal solar orientation for accessing solar gains since the building's long axis is not facing south. It's facing either east or west. B, optimal solar orientation for receiving passive solar gains since the building's long axis is facing south. And then C and D, optimal solar orientation may still be achieved with the building's long axis facing within 30 degrees of south. So if you get that 30 degrees of south, that's still optimal. So now we'll get into a little bit about mechanical equipment examples in the Part 9 buildings. So you have a wide range of mechanical systems that may be used to comply with step code energy targets. Selection of mechanical equipment options are shown for guidance. However, there are many other systems which may be chosen. Mechanical designers should be consulted when selecting systems for Part 3 buildings. So, some areas you're limited as to what energy you can use. I know like up the Columbia Valley, they don't really have natural gas service. So you're going to be limited there. You're either going to be using electricity or maybe even renewables. So here you have, a few examples of what some typical mechanical systems. Up on the top floor, you see some electric baseboard. You have your hood range, your dryer. Looks like you have a heat pump or air conditioner outside there. Some more baseboard in the basement, and you have a forced air furnace and a mechanical ventilation system. Looks like you even have a drain water heat recovery for the hot water tank there. So this is another table that can be found in the Builder Guide web tool that shows how you can reach different steps using a heating system, gas furnaces, electric baseboard, air source heat pumps, and with or without drain water heat recovery, gas storage, electric storage, on-demand gas, all the different types, and you know, what different steps you can meet using those systems. So now we get into detailing and sequencing. So that kind of relates to your building plans and also how you're going to finish the building enclosure, getting towards the end of the construction process. Detailing is one of the most important aspects of designing an airtight enclosure. Detailing the interfaces and penetrations, because this is where discontinuities are most likely to occur. While the individual air barrier materials and components provide control of air movement for each individual assembly, how and where each assembly intersects, and the continuity of the air barrier across these joints should be the focus of the detailing work. You know, this is kind of hard sometimes to translate to the different trades that may be on the site. You know, you could assemble an amazing continuous air barrier, and then all of a sudden maybe an electrician or a plumber comes along and starts poking holes in the interface, and they weren't consulted on how to seal those penetrations properly and make it continuous with the air barrier. A best practice design technique for ensuring continuity of the air barrier is to draw a continuous line around the enclosed space. This can help identify the air barrier on building plans, sections, and details. The line should continue around the entire enclosure and connect back to itself with no discontinuities. It should be possible to trace the air barrier without, as it were, lifting one's pen off the paper. The same concept applies to individual detail drawings as well. A detail should be prepared for all air barrier interface locations, clearly showing how continuity is maintained. Reviewing these transitions early on and collaborating with the affected trades, there we go, collaboration is important, will allow locations with constructability or sequencing issues to be identified and help determine if a revised detail is necessary. Assemblies with interior air barriers must account for all the potential interruptions and interfaces at the interior face of the building. Details for these locations should include all necessary components and products and basic installation measures to provide a continuous air barrier across all elements of the assembly. For example, air sealing using spray foam at the interior frame cavity must be combined with sealant across all joints in the wood framing, such as studs and built-up plates, no matter how tightly fitted they are. So this is a really important part of the design and building process. I'm just going to bring up this. Okay. All right. So here's some examples of that detailing, examples of air barrier lines of continuity. You've got the top of the wall, the punched window, deck, balcony, surface penetration, base of wall at foundation, foundation wall at slab. You want to make sure that you really are sealing all those penetrations and where those joints meet. So detail, it's an integral part of the overall design process, even in the early stages of design development. It should be used to inform and develop the overall design, while there is still flexibility in placement and configuration of elements. Like, we know sometimes these things change, right? You know, you have a plan, you go to build it, and then all of a sudden, you know, you can't put, say, the HVAC equipment where you wanted to put it. It has to go somewhere else. You want to make sure you're sealing all those joints, and even if they change. Leaving discussion of details until later in the design process could lead to complicated or costly corrective measures. So, sequencing details should consider construction, sequencing, and overall robustness. For example, wherever possible, Air barrier transitions in wood frame construction should be designed to allow complete construction of the primary wood framing before installation of the air barrier components. This way, the work of different trades can be separated and the air barrier installation can be more easily coordinated. So consider installing exterior elements not integral to the enclosure or structure using standoffs and intermittent attachment points. This can allow the air barrier to only be interrupted with point penetrations rather than extended interfaces like at balconies or roofs. 3D sequence drawings detailing may require three-dimensional drawings to convey air barrier transitions, both for design development and as part of the construction documents to convey all aspects of an air barrier interface. The most critical locations are often difficult to illustrate on 2D drawings alone. So this may be a limitation. If you only have 2D drawings, you may not be able to, get that continuous air barrier in the design process anyways. So here are some examples of 3D window installation sequence drawings, showing how the framing fits in with the wall assembly and how to properly seal those interfaces. And this is also in the Builder Guide web tool. So some common detailing deficiencies. Common deficiencies and challenging areas of exterior air barrier installation can occur at all areas of the air barrier system. The integrity of the air barrier relies upon the quality and completeness of the installation work. Some common air barrier deficiencies and likely deficiency locations include structural and surface penetrations using sealant and membranes, wrinkled fish mouth incomplete membrane laps, roof to wall and other interfaces with various transition materials, your roof and ceiling penetrations, window membrane and perimeter sealing, above grade to below grade transitions, and complex building forms and enclosure shapes such as fin walls and projections. So these detailing deficiencies can be avoided by using comprehensive detailing at the design stage and employing proper quality control and insurance measures during construction. On-site quality control of air barrier installation is a complex process. It's fundamentally important to achieve an airtight building and requires substantial oversight. Although the design documents may include details and instruction for all air barrier interfaces and penetrations, the builder is ultimately responsible for ensuring that all aspects of the system are installed and complete. Site mock-ups serve to demonstrate the air barrier installation processes, and regular reviews of the air barrier installation promotes consistent and complete work as part of the ongoing quality control process. The building enclosure consultant should be notified with sufficient time to review the air barrier, especially at critical details throughout the construction process. However, the consultant will not always be present, and there is a risk of discontinuities being missed or created in the air barrier throughout the construction process. So this is maybe something we don't see on building sites, an air barrier consultant. It could be a relatively new thing. Successful approach to mitigate the risk is to designate an air boss who is a member of the construction team responsible specifically for the air barrier. This person should be appropriately trained on and knowledgeable of air barrier strategies, the specific air barrier systems being used on the project, and requirements for building air tightness testing. So like I mentioned before, good time to do that air testing is after all the mechanical systems and equipment and the building assemblies have been installed, but before your siding and your interior finishing happens. So, if you see some deficiencies, maybe an on-site contractor goes around, sees some deficiencies where the air barrier has been compromised. In this example, you have, a roof assembly that hasn't been properly sealed. So, or it's been damaged in some way, so report the damage to the site superintendent. So now we're going to get into some of the mechanical systems. Whoops, there's that slide I was talking about where the roof assembly is kind of compromised your air barrier. So now let's talk a bit more about mechanical systems and equipment. Mechanical equipment and systems of building can have a large impact on its energy efficiency and overall energy consumption and have a large impact on the building equipment and systems metrics. The required capacity of the mechanical equipment and systems will vary with the performance of the enclosure and vice versa. So here are some examples of mechanical equipment and systems that may be used to reach various steps of the step code. This information is not intended to limit the use of any mechanical system or specific product. Both Part 9 and Part 3 buildings can use a wide variety of options as long as the systems are modeled for compliance with step code metric targets. Furthermore, the operating efficiencies that can be achieved with the different systems are not the sole indicator of their appropriateness for use in high-performance buildings. So house as a system. It's imperative to understand that building components, mechanical equipment, and occupants work as a system. When incorporating an enclosure-first approach, the thermal performance of a building is designed to reduce thermal losses and thermal gains throughout the year, which reduces the required capacity of heating and cooling equipment. Furthermore, the mechanical systems can be more easily controlled where the losses are reduced, and the systems can be optimized to further reduce the energy use of the building. For example, with an airtight enclosure, the code required minimum ventilation level is more easily accounted for and controlled since indirect ventilation through building air leakage is reduced. Where an energy-efficient ventilation system like a heat recovery ventilator is used, the energy load required to heat the incoming outdoor ventilation air can be minimized. Here, the enclosure and the mechanical equipment in combination provide energy-efficient building operation. So, an example solution, a house with a high-performance enclosure where an HRV provides healthy indoor air quality while recovering heat from the exhaust air. Makeup heat is provided by electric baseboards. So sizing of the mechanical equipment. Heat loss and heat gain calculations are the basis by which the mechanical heating and cooling systems are selected. In effect, all sources of heat loss, the building enclosure, ventilation, etc., are combined with sources of heat gain, occupants, appliances, heat recovery, etc., in order to estimate the needed output of the heating and cooling system. For heating, this is related to the TEDI metric. The required capacity and efficiency of the domestic hot water, DHW, and heating, ventilation, and air conditioning, HVAC systems depends on building size, end use, fuel choice, and energy target. The energy model used to evaluate a building's performance may also be used to size mechanical equipment and systems. As with the building enclosure, there are many possible paths and system choices that will enable the achievement of each step in the step code. Part 3 buildings will require professional mechanical design of all systems in the building, including the domestic hot water and the ventilation system. Large buildings can produce complex scenarios due to more significant internal heat gains from occupants and equipment, unique heating and ventilation requirements based on each individual suite, and the possible need for large central equipment that serves the entire building. So what's an industry best practice? Both the Thermal Environmental Comfort Association, TECA, and the Heating, Refrigeration and Air Conditioning Institute of Canada, HRAI, provide guidelines and courses for the design and installation of heating, cooling, and ventilation systems. More information is available at teca.com and hrai.ca. TECA and HRAI have explicit methodologies with worksheets and software for heat load calculations, that should be used for heating and cooling system sizing to ensure that load estimates are completed appropriately. So the HVAC contractors are probably going to be using these metrics, using these websites. They often too will use the energy modeling report with the sizing of the building, and the energy modeling software can generate certain reports that help them size their equipment according to the heat gains. And so also this HR, AI, and TECA are very useful tools for, you can enter in the certain model numbers of the equipment and see if you're going to be meeting certain targets and how to properly size the equipment. So, installation and commissioning. Careful attention should be paid to the design, installation, and commissioning of mechanical systems. Installation considerations are specific to the equipment type and should always follow manufacturer specifications and industry best practice guidelines. Post-installation commissioning will ensure that the mechanical systems are functioning to their specific efficiencies. So, you don't want to oversize or undersize this equipment. Mechanical equipment sizing is based on the sources of heat loss, the building enclosure, ventilation, etc., and the sources of heat gain, your occupants, appliances, etc., and the presence of heat recovery, HRV, domestic hot water, heat recovery, etc. Heating and cooling. The energy used for heating and cooling in buildings can be reduced in two ways. One way is by increasing the thermal performance of the building enclosure, an enclosure first approach. We've talked about that before. And the other is by choosing more energy efficient mechanical equipment. To reach the lower steps of the step code, either or both approaches can result in compliances. For the upper steps, both approaches are likely necessary. Gas furnaces, baseboards, heat pumps, and hydronic systems can all be used to meet the step code performance targets. So, gas furnaces. If you're using a forced air gas furnace, which are very common for Part 9 buildings, the code requires high efficiency condensing furnaces with efficiencies of at least 92%. You don't see that much anymore. They're at least 96% or higher these days. The energy efficiencies used in Energy Step Code 2018 metrics research full report were 92% and 96%. However, furnaces currently available on the market reach up to 98.5% efficiency. High efficiency condensing furnaces use two heat exchangers to extract heat energy from the combustion of fossil fuels, natural gas, propane, oil, to heat the air. The incoming air is generally both recirculated, return air from the building, and make up ventilation air. The energy demand of the furnace is based on the amount of air that must be heated to condition the home and the temperature difference between the incoming air and the temperature it must be heated up to. The furnace energy demand can be optimized by increasing the temperature of the ventilation air entering the system using heat recovery, or by using a dedicated ventilation system that uses heat recovery. So here's an example. You have a furnace, combined with heat recovery ventilator to improve energy efficiency. Heat pumps are going to do this as well. So electric baseboard, you don't see this as often, but sometimes this is used to heat homes. They're common heating systems for both Part 9 and Part 3 buildings and have an efficiency of 100%. Electric baseboards generate heat by electrical resistance and a heating element. The heat is then distributed by radiating fins. They can be operated individually, which allows for easier operation in buildings with multiple zones. Buildings that use electric baseboard heating systems must provide ventilation through a dedicated system because baseboards do not provide ventilation air. Furnace combined with a heat recovery ventilator to improve energy efficiency. Electric baseboards can be controlled individually. Operating cost. While each heating and cooling system offers different benefits, reduced operating costs for the end user may be worth considering. This cost optimization approach is referred to as net present value. So, you know, from what I can tell, electric baseboards are probably one of the most expensive ways to heat a building. So it would help if you're using those to have different zones, to have a heat recovery ventilator, so they're not always operating all the time. And that's the idea, is that baseboards can be controlled individually and they can be used to heat different areas of the house. So hydronic systems, they can be used for heating, cooling, or both. A fluid is heated and are cooled centrally, then piped through a building to terminal units. The terminal units are commonly hydronic baseboards, fan coil units, or radiant floors. There are many options for the central heating and cooling plants, each with different efficiencies and benefits. For example, the central heating plant can be a natural gas boiler coupled with a chiller. If both heating and cooling are desired, boilers typically use combustion to heat the liquid, while chillers generally function through a refrigeration cycle to chill the liquid. Alternatively, heat pumps can be used for low temperature radiant systems, both for heating and for cooling. The domestic hot water system can be coupled with a hydronic system. Low temperature radiant systems can be used in buildings with high thermal performance. These systems require lower water temperatures throughout the system and thus are paired well with heat pump water heaters, which have lower maximum water heating capacity than traditional boilers. Note that radiant systems may increase the risk of overheating without proper controls and commissioning. This increased risk is most relevant for buildings with very high performance enclosures. Note that this is important to properly commission all systems in any installation. So here's an example with a hydronic system using a boiler and a chiller to provide both heating and cooling. So heat pumps. Heat pump is a device that circulates refrigerant and absorbs and releases heat through evaporation and condensing of the refrigerant as it travels between the indoors and the outdoors. It operates in a similar way to a traditional air conditioner, but its function can be reversed to provide heating as well as cooling. Heat pumps can operate at much higher efficiencies than other typical residential heating and cooling options, in some cases over 300% efficiency. Heat pump efficiencies are measured in coefficient of performance, COP, where a 300% efficiency would be denoted as COP 3.0. The most common types of heat pumps are air source. However, ground source heat pumps are also available. Air source heat pumps extract heat from the outside air during the heating season, and they extract heat from the indoor air during the cooling season. Ductless mini-split systems are air source heat pumps, which are commonly used to control temperatures in individual rooms or spaces by heating or cooling air-to-air systems. Larger heat pumps are generally used as part of a central heating or cooling system in larger buildings. Cold climate air source heat pumps are specifically designed for cold climates and can extract heat from the air down to minus 35 at about the same efficiency as electric baseboard heaters. Ground source heat pumps draw heat from the ground or water in the heating season and return heat back into the ground in the cooling season. Ground source heat pumps are also known as geothermal, geo-exchange, or earth energy systems, and are often combined with a central distribution system, like a forced air furnace. Sewage heat recovery is another type of heat pump system that extracts heat from wastewater. These systems can be used for either domestic hot water or for space heating. So here you have an example of an air-to-air heat pump system with multiple interior fan units. So that would be a mini split or a ductless system.
So can you have a heat pump that's a natural gas backup?
Yep.
And is there a big cost premium for the cold climate heat pumps, do you know?
The cost is definitely much greater for the cold climate ones.
Okay.
There's also, greater benefits. There's greater rebates available because it'll help you reach that
Right, okay.
that higher step with that. Yeah. heating and cooling metric. When I'm working with existing homes, people that are getting the cold climate heat pumps are receiving maximum rebates.
Right, okay.
Yeah, for their upgrades, and they're highly efficient.
Sean,
yeah.
Can you explain how heat pumps work? Like when if the air's
Yep.
in the wintertime, the air is a lot colder outside than it is inside the house.
Yeah, that's right. And so it's extracting heat from the air. It's and the way they're incredibly efficient at doing that. They can extract heat from air on a 32-degree day or a -20 day, and the efficiencies aren't going to vary that greatly from those temperatures, right? And so when it's extracting that heat, it's passing it through the heat exchanger that's in the coil of the system, depending on whether it's a central system that's piped into your ducting or whether it's a ductless system. And so that extracted heat from the air is passing over that heat exchanger, and then the heat exchanger just works as hard as it needs to heat up the air to where the temperature is set, basically, and it pumps it in through the house. And it's using the fans to either send it through a ducted system or these individual heating units that are in the ductless system that are placed in each zone. And it's pumping that air throughout the house. And if it's sized properly, then it's going to work at its maximum efficiency to heat that air. And then that refrigerant is reversed in the coil. And now that, instead of the exchanger or the coil providing heat, it provides cooling.
In summertime?
In the summertime.
It provides air conditioning as well?
Yeah, that's right. And so that the function is reversed, and it's going to be extracting heat outside of the interior of the space and exhausting it to the outside air and then cooling as it goes in. I think we may get into a little more detail too on how they work. Maybe not here. But Natural Resources Canada actually, and through their Greener Homes website, has a very detailed publication that goes into really good detail on how these units work. I can, if you get me your email, I can send you that publication as well. Yeah. So let's talk a little bit about ventilation. Oh yeah, let's just take a break here then for a few minutes before we get into the next section. Ventilation, we've talked about the need for getting an airtight continuous air barrier to meet certain performance requirements, but with that increased building air tightness comes the need for sufficient mechanical ventilation to ensure a healthy indoor environment for building occupants. A well-designed and properly installed system will provide the right amount of ventilation and can be used to save energy. In Part 9 buildings, various ventilation systems can be used, but each type must provide direct ventilation to each bedroom and living space. Natural ventilation is permitted during the non-heating season using operable windows, but a mechanical ventilation system must be used during the heating system. So we see this is when we need these mechanical ventilation systems the most, is during the winter months when we're using a heating system to heat our house and we have the building envelope sealed up. It's pretty much 6 months out of the year in this climate zone. Yeah, could be turning on our furnace in October and also again in May. So yeah, that's pretty typical. So one way to provide this ventilation is through a dedicated air inlet and exhaust fan. Dedicated fresh air inlet combined with a central ducted heating system and an exhaust fan can serve as an effective basic ventilation strategy, especially for Part 9 buildings. This strategy uses the ducts for the heating system and a continuously running circulation fan to supply fresh air to all living areas. Even if the heating system is not running. At the same time, a continuously running exhaust fan, such as a bathroom fan, extracts stale indoor air. High efficiency fans can be used to minimize energy consumption of the fan operation itself, though the energy required to condition the ventilated air is often a greater energy load for the building. In this system, the ventilation air must be conditioned by the building heating equipment, and the greater the temperature difference between the outdoors and the indoors, the greater the energy demand for this process. So here's an example. You have ventilation with a continuously running exhaust fan and a dedicated air inlet. It's a very simple system. So make-up air systems. Make-up air systems use a central supply fan to provide ventilation air throughout a building. These ventilation systems are commonly used in large buildings and consist of a central make-up air unit, MAU, with ducting supplied to all spaces or units in the building. The MAU also conditions cold air to comfortable levels before it is supplied to the building. Typically, these units are gas-fired and heat the air through a heat exchanger. High-efficiency condensing MAUs have efficiencies above 90%. Alternatively, air source heat pumps can be used for both heating and cooling and can offer efficiencies above 300%. A make-up air unit can also be combined with an HRV to improve its efficiency. The BC Building Code requires direct ventilation to each living space. Thus, indirect corridor ventilation strategies, such as pressurized corridors, are not acceptable. The central make-up air system must be installed with ducts that supply the ventilation air directly to residential units. So here we have an example of a central make-up air unit in a multi-unit residential building. So, ventilation heat recovery ventilator, HRV, or an energy recovery ventilator, ERV, can be used to recover energy from exhaust air. These devices use a passive heat exchanger to transfer heat between outgoing exhaust and incoming supply air systems, or supply air streams within the ventilation units. Supply air is typically ducted directly to each living area and exhaust air from bathrooms and kitchens. In heating climates, HRVs and ERVs are primarily used to recover heat from the exhaust air to temper the supply air, but they can also work in reverse during the cooling season. The heat transfer effectiveness typically ranges from 60 to 85%. HRV and ERV systems provide continuous, balanced, energy-efficient, and comfortable year-round ventilation to homes. Additional benefits come from air filters within the units, which filter out pollutants and pollen. So that's definitely a benefit. You can install these systems with air filters, which we've seen in fire season can be pretty important. We get filtered air coming into the house. In multi-unit buildings, HRVs and ERVs can be installed in each suite or may be located centrally and ducted through a central ventilation system.
So that efficiency of 60 to 85% is no ringing hell at all. That's in terms of efficiency.
Yeah, that's just solely the heat recovery ventilator unit. Right. Yeah, that doesn't take into account the other systems, which may be much higher in efficiency.
Right, okay.
Yeah.
So if you have that HRV connected into your central furnace.
Yep.
It uses that duct system, but that wouldn't change the efficiency at all, would it?
No, it wouldn't change the efficiency of the actual heating system.
Okay.
Yeah.
Or the efficiency of the HRV either.
Right, exactly.
Okay.
Yeah. They're still going to be operating on that 65 to 85%, which is also taken into account in those step code metrics that are used by the energy modeler. Yeah. So HRVs and ERVs use a similar system, but the ERVs also transfer humidity between the supply and exhaust air streams. A specialized heat exchanger called the enthalpy core allows both heat and moisture transfer between air streams without cross-contamination. The ERV can be used to lower the humidity of the incoming ventilation air during warm, humid periods by transferring moisture from the supply air to the outgoing exhaust air, assuming it has lower humidity. It can also be used to transfer the humidity of outgoing air to incoming supply air during cold and dry periods. ERVs are generally more common in severe climates where humidity levels reach upper and lower extremes. So not as popular in drier western climates. The moisture transfer is intended to improve occupant comfort by maintaining comfortable ambient moisture levels. It can also reduce the need for air conditioning or humidifiers, which contribute to the overall energy use of the building. HRVs generate condensation, which should be plumbed to drain. ERVs do not generate condensation and do not need to be plumbed to drain. Note that CRVs, central recirculating ventilators, use a similar ventilation arrangement as HRVs and ERVs, but without the efficiency of heat recovery, and instead use recirculation and direct fresh air intake. So here's some examples too. We've got ventilation on the left here with the heat recovery and ducting throughout. On the right, we have a central ventilation with heat recovery in a multi-unit residential building. So let's talk a little bit about domestic hot water, because they do take up some energy. The heating of domestic hot water can account for 15 to 35% of a building's energy use, depending on the building type. Domestic hot water energy use may be reduced by selecting energy-efficient equipment and systems, as well as drain water heat recovery. Incorporating low-flow fixtures, shower heads, and faucets is a great way to reduce hot water usage, but is only accounted for in Part 3 energy modeling. So some tank types. Conventional domestic hot water heaters typically heat the water with a gas boiler or an electric coil, then store the heated water in an insulated tank sized to the demand of the building. It's recommended to have at least a condensing efficiency natural gas boiler of 90% or higher. Recommended. For higher efficiencies, air source heat pump hot water tanks can be incorporated that can go to 300% or greater. Furthermore, hot water tanks may be heated by site-generated energy through heat pumps or solar thermal systems. The domestic hot water distribution pipes may be designed with recirculation and heat tracing to maintain water temperatures throughout the building. This approach is not very energy efficient, and a more efficient way to provide domestic hot water in multi-unit residential buildings is by equipping each unit with their own hot water heater, or maybe even tankless systems. So here's tank type heater with drain water heat recovery installed. Tankless. Tankless hot water heaters can be used as a domestic hot water heating system for houses, as well as in-suite in multi-residential unit buildings. This type of water heater is also referred to on demand and instantaneous, as the water is heated as it is used. So, which sometimes can be an issue. If you have long runs, it takes longer for that hot water to reach the tap, and some people don't like that. Tankless heaters are generally condensing efficiency natural gas. For larger households, multiple tankless water heaters may be required to meet the hot water demand for multiple uses simultaneously. For example, running the dishwasher and taking a shower at the same time. Tankless water heaters work well in individual suites of multi-unit residential buildings as they take up minimal room, allow the occupant direct control of their hot water usage, and reduce the need for substantial plumbing installations throughout the building. So there's an example there of multi-unit residential building, each having their own system. So what's drain water heat recovery? This is another way to reduce energy use from the domestic hot water system. So it's recovering heat from the wastewater. This is an effective heat recovery strategy in residential buildings due to their high shower usage. Drain water heat recovery typically works through installation of a copper section of pipe installed in line with the main domestic drain pipe, the drains from showers, with another copper pipe heat exchanger wound tightly around it. The copper heat exchanger is connected to the supply line of the water heater. It extracts from the drain water running along the walls of the drain pipe, and it raises the temperature of the incoming supply water. Sewage heat recovery uses heat pump technology to extract heat from wastewater. This system is mainly used in larger residential buildings. So, auxiliary equipment, mechanical energy use intensity for Part 9 buildings and the total energy use intensity for Part 3 buildings each require that auxiliary HVAC equipment be accounted for in overall energy use. Auxiliary HVAC equipment generally includes fans, humidifiers, and other devices that are not directly accounted for in the heating, cooling, ventilation, and domestic hot water use. All HVAC auxiliary mechanical equipment like fans should be high efficiency to help reach the total energy use intensity targets. Additional loads included in Part 3 TEUI metric note that receptacles, appliance, and lighting load must also be accounted for in the total energy use intensity. Energy efficiency products should be used wherever possible to help meet these targets. These include LED lighting and high efficiency appliances. So, a few examples, your Part 9 mechanical energy use intensity, that's space heating, space cooling, service water heating equipment and auxiliary HVAC equipment. And then your Part 3 buildings total energy use intensity, you have space heating, space cooling, service water heating equipment, auxiliary HVAC equipment, and also includes your miscellaneous receptacles and appliances and lighting. So this pretty much takes us to the end of our presentation.